My name is Jordan Mirocha from JPL, and I hope to give you a quick sense of some of the kinds of science that we're going to do with the SPHEREx mission. So I'll just start with maybe the obvious question, which is just what is SPHEREx? So it's an acronym. We love acronyms at NASA and at JPL, and it stands for the Spectrophotometer for the History of the Universe, the Epoch of Reionization, and ICE's Explorer. So there's a lot going on there to unpack, and I'll try to do that at least a little bit in the next 20 minutes or so. So each of these key phrases represent one of our science themes. So we actually have 3 different science teams within the SPHEREx collaboration indicated here. And just in the interest of time, since our time is short this evening, I'm just going to focus on one of them, this galaxy formation theme. But I hope in the coming months or years, we can get other members of the team to come tell you about these other exciting themes. Okay, so that's what SPHEREx stands for. We are what's known as a NASA medium class explorer mission. So what that means is that in the kind of grand scheme of things, we're pretty cost effective. If you've heard of missions like James Webb Space Telescope or Roman, these tend to be projects that are developed over decades and cost many billions of dollars with a B. And missions like SPHEREx are on the smaller side. So there's another category, SMEX, for small explorers. And actually, we're sharing a ride or sharing a launch vehicle with this mission called Punch, which is also very interesting. So a third quick thing to know about SPHEREx before we really dive into the details, that this is a near-infrared telescope. And so we actually are observing wavelengths of light or colors that are just beyond what we can detect with our own eyes. So it really is a unique window into the universe. So as Stacy mentioned, this is a really exciting time for the project. Our launch window opens actually 2 weeks from today at 7:09 p.m. On February 27th. So I hope you will keep an eye on the news to keep track of launch and how things go as we begin our operations. So we're launching from Vandenberg Space Force Base in California, just a couple-hour drive north of Los Angeles. And we're launching into what's known as a low Earth or a sun synchronous orbit. This is about 400 miles above the surface of the Earth. And we straddle this day-night terminator line of the Earth. And the reason that we do that is because we need the sun to power the spacecraft through solar panels, which you can kind of see here. But because we're a near-infrared telescope, we also want to avoid anything that produces heat, so the sun and the Earth, which could otherwise contaminate our images. So what this animation is showing you is how we conduct our survey, just using a single one of our detectors as an example. So this kind of semicircle you're seeing is the region of the sky that we're able to see at any given time while simultaneously avoiding the sun and the Earth. And within that little window, we're taking roughly 2-minute exposures with our instrument. But in order to keep the sun and the Earth out of view, every few exposures, we actually have to take a big step to keep up with the orbit of the spacecraft, which leaves gaps in our coverage. So you might think, well, that's a problem, and we're going to map the sky. We'd like to avoid having gaps in our map. And it turns out that as we progress through the survey on subsequent orbits, we naturally fill in these gaps that are left behind on the previous pass. So we are really mapping the full sky, every single pixel, over the course of about 6 months or so, which is what you're seeing here dramatically sped up. So we map the sky every 6 months, and our nominal mission lifetime is 2 years, which means we will obtain, by the end of the survey, 4 all-sky maps in the near-infrared, which is going to be useful for a wide number of science applications. So because SPHEREx is a space-based near-infrared observatory, I thought it was probably worth taking a minute to compare and contrast with another space-based near-infrared observatory that you may have heard of, the James Webb Space Telescope, launched just a couple of years ago. So JWST, as you can see here before it was launched, JWST is the biggest space telescope that's ever been constructed. So you can get a rough sense of the scale from the people in this image. Something that I want to draw your attention to is that the James Webb Space Telescope primary mirror, the light collecting mirror, is huge, and it's composed of individual hexagonal segments. Now, each of these hexagonal segments you're seeing is about 1.3 meters in diameter. Okay, so comparing this now with SPHEREx, our entire spacecraft is only about 2 meters tall. So it's sort of comparable, at least in its height, to one of these people in the laboratory here. And the telescope, sitting inside these cones, which help us avoid the light from the sun and the Earth, the telescope is only 20 centimeters in diameter. So if I draw what that looks like compared to just a single one of these JWST mirror segments, it really drives home the point that the SPHEREx telescope is actually very small. It's comparable to a good backyard telescope, at least in terms of its total light collecting area, the size of its mirror. Okay, so why go through the trouble of building this small telescope and launching it into space when we now have the James Webb Space Telescope? So the size of the mirror isn't the only consideration when building a telescope. Another really important consideration is just how big of a piece of the sky the telescope sees at any given time. So while SPHEREx is a very small telescope, it has a huge field of view. Okay, so I'm trying to give you a sense of that in this slide. These three boxes here indicate the apparent size of our detectors as they see the sky. And I've included here the full moon as a kind of reference point. Okay, so the full moon is about half a degree on the sky. So we have hundreds of full moons of area that we can cover in any individual exposure. So if I then overplot the field of view that JWST sees in any given moment, it's about 1 pixel on this scale. You can barely distinguish it from a little speck of dust on your computer screen or your TV screen. Okay, so the punchline here is that SPHEREx is a survey telescope and JWST isn't really, okay? And so they're very complementary to each other. And so whereas JWST can really zoom in on galaxies and provide us with these beautiful and intricate details, like spiral arms and these nearby interacting galaxies, these galaxies themselves are actually huge. They're, comparable in size to the Milky Way, but they're far away. So they don't actually subtend a very large angle on the sky. This particular system, if we could, see it with our naked eye, would be small, even with respect to the size of the full moon. So if I zoom out and try to give you a sense of the sky as SPHEREx sees it, the universe looks very different on these scales. Okay, so once again, I've brought with us the full moon for scale here. This is the angular extent of the moon as we see it on the sky. And the movie that you're seeing now is scanning through a simulation of structure in our universe, where the bright spots indicate regions where galaxies are likely forming, and the dark spots indicate regions where there's few, if any, galaxies. And frame by frame, we're stepping through distance here. So the movie began relatively close to us, and with each passing frame is moving further and further away. And what you'll notice is that the universe's structure on these scales is this patchwork of filaments that we refer to as the cosmic web. And so an individual galaxy or pair of galaxies, like I showed you on the previous slide, is completely unresolved on these scales. It's just a tiny speck of light. Okay, so we can learn a lot by mapping the universe on these large scales, just like we can learn a lot about individual galaxies by zooming in on them with James Webb Space Telescope. And so the circle that I've indicated on this movie is the size of the region of the sky that we're going to use in SPHEREx for our investigation of galaxies. So on these scales, we're so zoomed out that we often think of galaxies as just single pinpoints of light, and may even indicate them, as I have here, just with little X's. to mark the spot. And it's hard to remember sometimes that each of these little specks of light is itself a little island of hundreds of billions of stars. And just on these scales, we don't see that. But we see other things, right? We can see that galaxies are clustered. You tend to find them in groups. But there are also regions of the universe that are seemingly devoid of galaxies. These are known as voids, where few, if any, galaxies are found. But there is a problem with looking at the universe with wide field surveys like this. There's always trade-offs when you're building an experiment. If you're going to spend the same amount of observing time covering the whole sky, you're not quite as sensitive in any individual region of the sky, which means you can't see objects as faint as you would like. So one way of thinking about this is if I look at in the middle here now, where all the light in the universe is coming from, compared to where just the brightest galaxies live, you see kind of a different story. There's a lot more going on here in the middle column than is indicated just with the X's on the left. So a pretty good analogy that we like to use a lot to describe this problem is that the brightest galaxies in the universe are really just the tip of the iceberg. Okay, so most of the galaxies are just too faint for us to detect. And by us, I mean us in SPHEREx, but even in some cases, JWST cannot detect these galaxies. And so if I kind of superimpose these two images, you can see that the bright galaxies in the simulated universe do trace out this kind of filamentary structure where the light is coming from. But it doesn't get the whole story, okay? If you focus in on individual regions, for example, that appear to not have any galaxies, of course there is light there. It's just coming from galaxies that we can't see. And if you focus on different kinds of regions, this one in the magenta circle, again, has no discernible bright galaxies, but it still has light. And in fact, it has more light than the first region I drew your attention to. And we can keep going on and on here, looking at regions and seeing if the bright galaxies are really a faithful representation of the total light content. And the story here is that there's a variety of environments in the universe in which galaxies are forming. So as this movie kind of scans through a simulated field, we can see a region now where there's tons of bright galaxies. But just, a short cosmic distance away, there's a void where there aren't so many bright galaxies to be found. And really, there's every kind of environment in between. So by mapping the universe on very large scales, we really have the potential to look for all the different kinds of regions where galaxies are forming and evolving over cosmic history. So I've made a big deal about the fact that a lot of galaxies in the universe are too faint for us to see directly. So how do we actually learn about them if we can't take a nice image? So I have to say, I'm biased, but I think SPHEREx does this in a really clever way. So if we just, for illustrative purposes, focus on one of these regions from the movie I just showed you, there's a bright galaxy in the middle, and there's some faint emission nearby. In practice, the reason that we can't resolve out this faint emission into individual galaxies is just because our observations aren't perfect. We're taking a series of short exposures, and so we're limited in how much light we can collect in that short amount of time. Our detectors have noise, they're not perfect, and the list goes on. And so if you were to try to make this look like a real image, you might get something more like what I'm showing you here in the middle, where you can still tell that there's kind of a bright patch here with a bright galaxy, but the kind of fuzzy structure is harder to see now that I've kind of simulated a more realistic astronomical image. So what do we do? Well, one game we can try to play is to take advantage of this feature of the structure of the universe I mentioned earlier, which is that galaxies cluster together. If I see one galaxy, it's probably not alone. It's probably got many neighbors in its nearby environment. And so what we can do is if we were to look at this particular region of a map, we could say, let me look at how the brightness of the pixels near this galaxy vary. So what you'll notice here is this white line is showing an example distribution of pixel brightness values in this little box. And you can see it's kind of bouncing around, it's noisy. And that's frustrating because a lot of the galaxies in this image are actually comparable in brightness to a typical noise fluctuation, which means that, for example, in this case, I couldn't confidently say whether this bright spot in the map is a galaxy because I have other pixels who have similar brightness and no galaxies to be found. This is just a byproduct of noise in the image. But one trick we can play is to simply add up the light from all of these nearby pixels, and that allows us to average out the noise level and reveal the properties of these faint galaxies, at least in aggregate. Okay, so in this particular example, it turns out there's actually more light coming from these faint galaxies together than there is from this lone galaxy that we were able to detect. So that tells us that there's information in these maps beyond just where the bright galaxies live that we can extract if we're a little clever. So I want to pause here for a second to talk about what is perhaps the most novel thing about SPHEREx, which is really important when you're going to play games like this to reveal faint galaxy populations. And that's that SPHEREx observes in 102 colors. Now, this is really kind of groundbreaking approach to mapping the sky. Classic surveys on big telescopes tend to do a kind of two-step procedure where they map the sky very efficiently in broadband filters, or photometric filters is what we call them. This is basically mapping the sky in a red filter, a blue filter, a violet filter, for example, identifying galaxies in those images that are interesting, maybe because they're bright, maybe because their colors are interesting. And then if you want to get a more detailed view of those galaxies, you usually follow up with a different instrument on the same telescope, or maybe a different instrument on a completely different telescope to reveal more information. So SPHEREx is somewhere in the middle, right? We're observing 102 colors, but the really novel thing is that we're doing so at every single point on the sky, not just at the locations of interesting objects that we've pre-identified with photometry. So what that means is we can actually study the structure of these maps, basically how they vary on different spatial scales. And we can do that as a function of 102 colors as well to try to reveal not just where the faint galaxies in the universe are, but what are their properties? So what are their colors and how do they cluster? So my second to last slide here shows a pretty technical plot that tries to capture quantitatively the story that I just told you. And so one way of characterizing how much the patterns in these maps are fluctuating is through something called the power spectrum. This is a powerful statistical tool of the modern cosmologist. And what's being plotted here is basically how strong are the fluctuations in my map as a function of color. And there's a smattering of pre-existing constraints here from other experiments that tell us that at the bluer wavelengths in the near-infrared part of the electromagnetic spectrum, the fluctuations are stronger than they are at redder wavelengths. Okay, so that tells us something about the kinds of galaxies that are lurking beneath the surface in these maps. And the final thing I want to draw your attention to here is these staircases towards the bottom. These are estimates for how sensitive we are to these fluctuations. And the red region indicates a prediction for how much galaxies during the universe's epoch of reionization are expected to contribute to these fluctuations. And so the fact the red region lies above our sensitivity estimates tells us that we think we can detect galaxies very early in cosmic history. So I don't have time to get into the EOR in too much detail, but I'll just leave you with this cartoon picture describing kind of the formation of structure in our universe, starting with the Big Bang all the way on the left and ending with present day all the way on the right. So the epoch of reionization is a period in our history that's probably about the first billion years or so after the Big Bang, when galaxies are really first starting to form. And it's really interesting. The universe was a really different place back then. And as these first sources turned on for stars and galaxies, they injected a lot of energetic radiation into the cosmos for the first time and transformed their environments as they grew. So this is the target of a number of observatories, not just SPHEREx, and is really one of the kind of final frontiers in modern cosmology and astrophysics. So, and the E and the R are the E and the R from the SPHEREx acronym that I showed you on the first slide. So we're hoping to present constraints on the epoch of reionization in the next couple of years with our data. So I hope I've gotten you excited about SPHEREx and convinced you that its approach to mapping the sky is really novel and powerful. And yeah, we're all very excited to start conducting the survey in just a couple of weeks after launch. So I'll leave it there, and I'm happy to take any questions that you have. Thanks for your attention.